All right. Hello, everyone. Welcome to lecture two of the Gyan course on innovations in infrared imaging. In lecture from now on, I'll start with a brief review of the what we discussed in the previous class. Just like for 1 or 2 minutes, I'll give you like an overview of what we discussed, which will help us that kind of help with continuity. Last class we discussed medical imaging technologies, why they are important, how they are useful, and what are the different categories and classes of these imaging methods. We saw that like at different lens scales, for example, if you want to go deep inside the body, the trade-off is that you'll have a higher resolution. So I talked about MRI and CT and ultrasound. So basically, today go a little bit deeper into some of the details of these like general classes of technologies. Um, and in the first half of today's class, I'll talk about all the working principles of some of these, and then in the second half, I'll start with a review of optics. What is a ray? What is a wave? And that kind of basic, starting with the foundational aspects of optics, because the focus of this class is infrared optics, infrared imaging, and so we need to understand light in order to understand the basic ideas about how to build imaging systems with light. Okay, and a crucial element that we discussed was for any imaging modality, we need to understand what exactly what are the physical properties that we are measuring. What physical properties allow us to interrogate the specific medical problem of interest. So it could be, for example, it could be in the case of X-rays, it could be absorption coefficient. In the case of ultrasound, it could be density, hard or soft, like parts of the tissue, and so on and so forth. Okay, so we need to know what we are trying to do first before we even start, and once we understand that, we will build a system. And there are several different aspects we need to think about as we go along. So this is a very framework for a medical imaging system. You have a source of light or source of radiation. It could be sound or light or something of that sort. X-rays, for example, is an electromagnetic wave. It goes through. Um, it There are several things. So something of interest. Say it could be like say the lungs or the kidney or like some part organ inside the human body. In between, like there is no straight line. Our body not transparent, and therefore in between, which will prevent or like obstruct the direct view of this particular organ. It could be something like clutter. It could be the surface itself, a change in the perhaps the refractive index or some property in between which changes. And after we have to figure out how to get there and like get our source like radiation to the target, and then when it comes back out, we have the same kind of problem. Then and you measure using a sensor or a detector. It could be a one point detector, it could be a line detector, it could be an array detector. But in different cases, we use different ideas and approaches to construct the system which has a source and a detector and something, the sample which you are trying to understand. That's the basic framework for most imaging systems. Okay, so with this in mind, I wanted to start off with an overview of four different classes of medical imaging tools. Okay, so one is what is called computed tomography or CT. Okay, so there are, if you go to most big hospitals these days, you will likely encounter this in so if a doctor suspects first you go to a doctor, and then the doctor like can order a test. So depending on your symptoms and depending on what the doctor thinks is the problem, he or she may say, okay, go get a blood test done, or alternatively, go get an X-ray done or a CT done or an MRI done or something of that sort. So that's typically how it works. You get some tests done. The test will tell the doctor, give him or her much more details of what is going on inside the body, and then that allows the doctor to make a decision. What is the medical problem, and what medicines or what exactly it could be physical therapy, it could be medicine, it could be some diet changes in diet, whatever the solution may be. So, like looking inside the body to figure out the problem is where all these things come into the picture. Okay, so that's the idea. So first, I'll talk about what's called X-ray CT, and then I'll talk about ultrasound, which does not use light, it uses sound, but the principles used here are useful for even light, as we will see a little later. Okay, and then the third one is what's called positron emission tomography. It's a completely different way of getting images from inside the body. This uses basically this uses radioactivity, as you will see. Okay, and the next one is what's called MRI, magnetic resonance imaging. Okay, that's also like it uses magnets. So this uses light of a high frequency, X-ray light. This uses sound. This uses nuclear radiation, radioactivity, and this uses magnets. Okay, so these are different big classes of imaging technologies that are very well known and used in most big hospitals in today across the world. Okay, so here is the first thing to note is that X-ray CT is a generalization. So this is CT or computed tomography. Okay, tomography means getting three-dimensional information. An X-ray is basically a projection. It's an image. So in about 1900, Röntgen discovered X-rays where there was some electrons hitting a metal, and that happened to emit X-rays. Nobody knew X-rays at that time. He put a finger, and there was a film of photographic film of some sort, and he saw that on the photographic film, he saw that his bones were visible. Accidentally, he discovered that, and then he discovered, okay, there must be some rays or something emitted from that the experiment he was doing over there, where electrons were hitting metal, and then X was unknown. So X rays there are some rays being emitted. You don't know what those rays are. He called them X. So X ray. That's how this came about. Okay, so X ray is basically some radiation which happens to be very high frequency electromagnetic waves, light of very high frequency, much higher than visible light, much higher than ultraviolet, even. So it's even higher than all the light commonly the white light that you see here. It's higher frequency than all of that. Okay, and so what does an X-ray do? Say X-rays come in this way, and it passes through, and basically it compresses, like it gives you an image, right? So although your hand is three-dimensional, the image is two-dimensional. So what is the relationship between the three-dimensional object and the X-ray? It's a projection. It integrates. It goes through and integrates everything that is in the path, and it's an addition of all the different absorption coefficients here. Okay, if there is a bone here and bones absorb more than other parts of the tissue, then you will see a kind of higher value in the X-rays. Okay, in other tissue which absorb less will give you a lower value. Okay, that's the basic idea. So this image on the left here is a typical X image. Okay, so this was kind of people recognize the usefulness and kind of usefulness of this in medical diagnostics. People use this for a long time, for about 50 years or so. but nobody knew how to get three dimensions. So if say there is like some parts of the body which are kind of just next to the bone, or some soft tissue like other than the bone, so you can see bone easily, but what about other organs? That's the question. Like nobody had an answer for years after X-rays were discovered. And technology was improving how to get better X-rays and what are the problems. So one of the disadvantages of X-rays is that it's radiation which actually can damage your DNA and it can actually cause harm. So too much X-ray exposure is also not very good. People didn't know it earlier, but over time they figured out that like sort of once or twice, once in a while it's okay, but constant exposure to X-rays is very harmful, and that's something that people discovered over time as well. So to get back to the question, of how do you figure out if there are lungs, for example? Lungs don't absorb X-rays as strongly as bones. So how do you get an image and three-dimensional image, volumetric image uh, of the of the body using X-rays? Okay, so that's that's when basically and it's called Hounsfeld and a few others figured out like some clever ways of doing what is called tomography. Okay, so in other words, getting three-dimensional images. The fundamental idea is as follows. So here you get have X-rays passes through the body, and you get an image, right? Now just turn this a little bit. Okay, pass the X-rays again and get another image. Rotate it a little bit. Pass the X-rays, get an image. Rotate it. Okay. So basically, for different directions, like you get images of the like get projections from different directions. Okay. And you get images for every direction. You get an image. Direction change the direction. Get an image. Change the direction. So you get a sequence of images where each correspond to different directions, and then you use some calculation, some computation to from these projections you can figure out the 3D structure. It's like as though say you have an object, you look at it just by looking at taking a picture from the front, you can't figure out the 3D structure. Then you see it from the side, you get one view. See it from the other side, you get a view, and then mentally you can kind of put together these pieces to figure out the 3D shape of the object, right? That's the idea. And there is a so in order to quantify this, use a computer to like at that time, in fact, they uh, like, computers were not easily available and not very powerful, but they still figured out how to do this. Oh, and because of the use of computers, it became much easier later on. But the basic idea is that you take these sequence of images, each from different directions, use some calculations, and then get the 3D volume image. Okay, and so yeah, so here is the object of this sort. You can another thing is you can either have the X-rays come through and rotate the object, or you can rotate the source in the detector. There is an equivalence between the two, right? So you can keep the object fixed and rotate this source in the detector, or keep the detector fixed and then rotate the object. So there is an equivalence between the two. Whichever way you use, both are fine, depending on whatever is easier for the experiment. And so basically, you you also limit this in kind of like first you limit it along one direction, three-dimensional object. You limit it to one slice over here, okay, and then keep rotating and get the image. And so it turns out, so Hounsfeld figured out that he got the Nobel Prize for this for medicine in 1965. I'm not 100% sure of the exact date, but he got a Nobel Prize. And so one of the things that he figured out was how to, from these projections, how to construct the 3D volume. And the answer happens to be what's called the projection size theorem. Okay, and what he says is that take these projections, take a Fourier transform of these projections, and thus the projection in the spatial domain is equivalent to a slice in the Fourier domain. Okay, that's the essence of the theorem it's called the Fourier slice theorem. It's called the projection slice theorem, and so on. But basically, you like kind of take the projection, take the Fourier transform, you put it together in the Fourier space at different angles, then take the inverse Fourier transform, you get the 3D kind of reconstruction. That's the essence of the idea. Okay, I'm not going to the kind of exact math of exactly how that works, but just want to give you a sense for what the idea is and so what the idea is with this approach. Okay, and yeah, so like I'm sorry, so the desired image of the inside of the body is computed projections this way, and you get actual images of this sort, where say this is so you can see that this is the chest area, and they have taken a slice across the chest in somewhere here, and these are the lungs, for example, over here. This is the kind of spinal cord. This is the spinal cord, and this are kind of the heart. This is the heart here, and so on. Basically, there are different organs which you can see, not just the bone. Although we are using X-rays, which typically were only now with this three-dimensional volumetric construction, you can see organs, all the other organs inside the body. Okay, that's this is kind of how the technology works. Yes. Mm-hmm. 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 So you can see the bones here, right? These are actually bones which are the ribs. So they are part of they are in this image. It's different. If you're looking at it from a cross-sectional perspective, they're around. And so yeah, so in 2D they'll all get like the one will obstruct the other. In 3D you can see both the ribs and what is inside the ribs and what is on the other side. Everything you can see in 3D. But in 2D, it will kind of like it's like say you have like uh, two plates like this, right? If you look from like and say there is a ball in the middle, just as an example. If I show you like this will be obstructing your view of the ball, right? But now if I rotate it like this, now in 3D you can see the ball, right? So from a different view, if you have 3D volumetric data, then you can see what is in the middle much more easily. Okay, that's the basic idea. Okay, and even though lungs and heart and other things have lower absorption, you can still see them with this kind of an approach. Any other questions? Yes. Mm-hmm. Correct. Yes. So this is essentially a map of absorption coefficient. If it absorbs, it will have higher. The exact color scheme. This is a gray color, like gray, black is 0 and white is 1, or something of that sort, right? You could use a different color scheme for that matter. But basically, it's a measure of like some things like bones, which will have higher value. Other things will have lower value. You can kind of adjust the contrast by adjusting this color scale and so on. But basically, lungs mostly has air inside, right? And so they will absorb less. And there is, so depending on what is there, you can kind of see what's going on. And the other thing is, if, for example, something in some organ does not have good contrast, you can't see it well because it doesn't absorb much. What do? You still do. And last time I talked about contrast agents, right? Like so basically you can inject something to the blood, which goes like, let's say some kind of a chemical, some which absorbs well. And when it is, let's say, it's flowing in the blood, and then it reaches some organ, and you can see the where that chemical is flowing, and that way you can get a map of that chemical, and that way you can also see, like, something which was previously has less absorption. This contrast agent can give you much better images of that particular organ. Okay, so that way, that is one way to see other, like, objects which are typically not seen. Good questions. Anything else? Any other questions? Okay. So the next imaging method I wanted to talk to you about is ultrasound. Okay, this uses sound and not light, but it's so the idea here is that you have what's called a transducer. Okay, basically, the the idea may be familiar, like, sort of the underlying principle is probably familiar to many of you. Okay, this is kind of how bats navigate. How many of you know how bats, like, move around and kind of figure out? We have eyes, right? We can see, but bats fly in the dark. How do they navigate? Anyone has ideas, or anyone knows how that, what they do? They use ultrasound, and what do they do? Mm-hmm. Yeah, correct. Yeah. So what you said, let me repeat that for those who didn't hear that. So they send out a pulse sound waves, okay, and it goes in different directions, and it reflects. Say if there is a surface, it reflects back, and so they kind of estimate the time it takes for the sound to come back. They have ears which can hear the ultrasound, and basically, by looking at how long it took for it to come back, and also the intensity of how much came back, they can figure out where the object is. Basically, they can kind of triangulate and figure out in if there is an obstacle somewhere, or if there is like an insect which they want to catch, or whatever it may be. So basically, that's the idea. So this is in the last class I mentioned time of flight imaging. So that's essentially what they do. So ultrasound is this ultrasound imaging is a version of that. Okay, so the same basic principle is used. So you, from the transducer here, you send out an electromagnetic wave, you send out an ultrasound wave. Okay, and different organs, like at different boundaries, they reflect. And by measuring the time it takes for the sound to come back, you know how far away from the transducer that particular obstacle where which reflected is. Okay, and by making these measurements, a sequence of measurements in different directions, you can construct the 3D structure of objects, of tissue, organs inside the body. So the next question is, why would why would an organ reflect ultrasound? And this is a general principle, not just for sound but also for light. And the reason, whenever there is like a barrier of some sort, or a change in the density. So when, say for example, a wall is an example, air has very little density, a wall has very high density, right? So something very soft to something extremely hard. So when sound hits wall, it bounces back. Whenever there is a change in material properties, there's a reflection. A change in the refractive index, there will be a reflection or scattering of light. The sound is similar. The biggest change is when you go from air to something which is dense, optically dense, or dense with respect to sound, or whatever. So basically, So whenever there is a change in this medium, like so in organs, so there may be kind of some gap, like one organ may have higher density than its surroundings. Some surroundings may be liquid, and then there is like an organ, and therefore basically whenever the sound change encounters this boundary, you get a reflection from those boundaries. Okay, so yeah. Mhm. Absorption is different. So this is just like it's a change in the material property. We are not thinking. Let's assume there is zero absorption at all, right? Like in the case of let's say glass, okay, a nice like kind of transparent glass, light hits it. So even if the glass is perfectly transparent and most of it goes through, there is some amount of it which is reflected, not because there is an absorption, but because there is a change in the refractive index. Just the change causes a reflection. It's not a matter of absorption. It's just because of the change in the uh, like the refractive index, that itself causes a reflection. Okay, or scattering. It could be reflection from scattering, but something of that sort happens. It's and if it absorbs, then additionally there'll be some other effects. But this reflection is just a consequence. Reflection or scattering is a consequence of the change in refractive index, or change in the speed of the like wave that is going. That's the idea. Okay, yeah. So this is like yeah. So this is one kind of approach to um, making measurement, like making depth measurements and getting a three-dimensional picture of the like object. Okay, and so yeah, so like it measures the reflectivity of the acoustic wave, and you get echo at different locations. Kind of like the wave you send can be focused so that you can get images from different points, and you change the direction in some way and get images from different directions, and then put together a 3D kind of a scene. Okay, so this is in a more it's a more direct imaging. Echo is placed directly, so this does not use computation as much as the computed tomography. It's just won't work without actual calculations. In this, you just need to know speed of sound, and then you need to know time, and you kind of calculate distance, right? Distance divided by time is speed. So therefore, you can distance is speed times time. You kind of know all these numbers. You can estimate the distance. That it's much lesser calculation. Okay. So what can this do? So depending on the speed of sound in the material that you're interested in. The speed of sound in air, it depends on humidity and a lot of other things. But ballpark something like 300 meters per second of that order of magnitude. But in solids, it's a bit longer. It can be more, maybe 1,000 meters per second or something uh, higher. But in general, in tissue, there is some number, an estimate of a number which you can a good estimate of in different materials what is the speed of sound is something you can measure quite easily. Then the other thing is, if you actually take those numbers and take the amount of time it takes, milliseconds or micro, you can actually you can make detectors which can measure that amount of so therefore the resolution, how much, so in this case, resolution means there are two layers which are one next to the other. Like there is a time, like echo from one, echo from the other. So the echo from one, if it is very sharp, and the echo from the other is very sharp, then you can distinguish the two. If they are such that kind of they are merged into each other and you cannot, they're combined and you cannot resolve them. So the limit of how close two boundaries can be, and you can still resolve them, that is called the limit of resolution, or resolution of depth resolution of ultrasound. So this resolution is of the order of a few like micro hundreds of microns to millimeters, depending on kind of depending on frequency of sound you use and if you have few other parameters. So you can make these measurements. So it's limited by the essentially by the frequencies that you use and few other instrument parameters. And yeah, so you cannot get very high resolution, but you can go few centimeters deep into the body. Yeah. So here is like kind of the relationship between oops, yeah, lambda equals, I think this typo here, like it was okay in the, yeah, so sorry about that, yeah. So basically, like the wavelength of light is essentially what determines resolution. And you can also improve the, sorry, yeah, you can improve the resolution by increasing the frequency. So, yeah, increasing the frequency reduces the wavelength and therefore improves the resolution. And also, you can get improved lateral resolution by doing some like by increasing the frequency as well. Okay, so you like so the advantage is like by if, what prevents you from keeping the frequency. The disadvantage is that the higher, as I mentioned just briefly in the last class, you will get worse penetration depth. So it won't go deep, very deep. Higher the frequency, the lower depth it will reach. So if you want to see something very reasonably deep, then as you increase the frequency, you will get better resolution, but you will lose how far you can see inside the body. If it's just below the surface, then this is okay. But if you want to go deep, you can't just keep increasing frequency and getting better resolution. There are these kind of trade-offs. Okay. Yes. That's correct. Yes. Mm-hmm. Mm-hmm. That's an excellent question. Yeah, that's correct. Yeah. So this increase in frequency is a relative term. For a small change in frequency, these are kind of the kind of effects. But so there are so the amount of X-rays like that are being absorbed. So basically, it depends on the essentially on the absorption coefficient. So like so let's say you take one wavelength and a slightly different wavelength in just in the infrared. You take a shorter wavelength and a longer wavelength. What I said is true. Kind of as you increase frequency, the penetration decreases. But that is fundamentally determined by the material property, which is the absorption coefficient. And so for X-rays, things absorb very less, and in that sense kind of it's that absolute value of the absorption coefficient which may make decide determines whether you see something or not. And in but it so happens that for X-rays they have low absorption coefficients and things go through. Okay, but like if you yeah take any single kind of modality and a small change from that wavelength, if you reduce the wavelength you will typically get higher resolution and lower penetration. That's basically what I was saying. Okay, because like it's like a small change in a local region. If you take globally, radio waves go through entire buildings, right? And like kind of like there are so you have to like kind of there are it depends the absorption coefficient of the building in essence. Absorption like so that's really and a general rule of thumb is that the absorption increases as frequency increases for small changes in frequency. So the other kind of the thing which ultrasound can do is like you can not only can you actually see changes in density, you can also visualize flow, say, of blood inside the body. Okay, so some many of you might have heard of the Doppler effect. How many of you know about the Doppler effect? Raise your hands if you all of you have heard of it. Okay, yeah. So basically, it's for just in case some of you don't know. So when you have, like, say, some sound, it hits an object and reflects back. So if instead of it hitting a boundary and coming back, if it is moving, then the frequency of sound that comes back is slightly shifted from what is incident. Okay, so then that, like, how fast it is moving determines what frequency change in the sound that comes. Okay, this is well known for, like, trains and kind of other things which like are emitting sound, and this has been known for a long time. But the crucial thing is that it's one thing to know it, it's another thing to use it in engineering to actually make a device which will be useful. And in this case, people have figured out to use the Doppler effect to make the sound uh, find the speed of the blood which is flowing inside, and get maps of the distribution of which directions, how the blood is flowing in what direction, and how, like, what then, like, so how much of blood is flowing and so on. Okay, so the Doppler effect can be used as a contrast mechanism to see the flow of blood with this approach. And the second thing is, how many of you have heard of speckle? You know what speckle is? So if you have a laser pointer or something, and you shine it on, so you have this random kind of, okay, there's a big dot in the middle, but there are on the side, you have these kind of dots which are quite random, and that is essentially called speckle. Okay, it's the random fluctuations in the distribution of light, which is light or sound. And so this also happens in the case of sound, and this can also be used as a contrast mechanism. It's used to create images. Okay, so we'll get back to the details of what is speckle and how it can be used in the context of light in a different lecture. So this is kind of high resolution. This is the kind of image you get from ultrasound. As you can see, like, something which is, so this is where the sensor and the source in the sensor are. So as you go along, so you can see that these regions here have a higher resolution. You can see that these, as you go deeper, you will kind of lose a little bit of resolution. Okay, that's kind of a trade-off that you make. Here you get better resolution closer to the scanner, and farther away there is a slightly worse resolution. And this on the right side is an image. So these colors over here use what's called Doppler. So this is they use the Doppler effect and figure out the distribution of blood. So it's kind of color coded to tell you what are the like kind of speed, centimeters per second speed of blood flow in different directions. And so you can get maps of the flow of blood as well with this approach. So remember that, like, sort of all these things that you learned in high school and in first few years of undergrad, like the principle, like kind of, for example, the Doppler effect and things of that sort. Every one of the ideas that you have heard of could be useful in some way to build devices. Like every phenomenon that you know of can potentially be used, and so it's your job as engineers to figure out, oh, I remember this from a long time ago, I studied it at some point, and but I've forgotten. But look at it and, okay, maybe I can use this idea to make people. Once people discovered ultrasound, people thought, okay, blood flow. If you use the Doppler effect, because there is of the change in frequency, you can somehow figure out the blood flow. Making the connection between ultrasound and the Doppler effect and blood flow, that's something requires a lot of imagination. And building stuff always requires imagination. Like, I'm sure many of you know each piece, but putting them together in a clever way is really where the kind of innovation comes into the picture. And as we go along, I hope you will catch on to some of these ideas that people have put together, and maybe you can come up with another new, different way in which you can put together ideas that you already know, so to build something new. Okay. Yeah. Hmm. Hmm. Potentially, yes. Yeah. You could. So it's always a trade-off. So engineering, like what you said, is right. So you could build array of ultrasound sensors in all different directions and kind of get a much better image in some way. But remember that this has to be used in a hospital, and like in practice, if somebody, a doctor, is holding this in their hand and moving it around, they can do it themselves and kind of move it by hand. In, like, if you really, um, putting one sensor instead of, like, say 20 different sensors around, it costs 20 times as much at least, or maybe like, and then it costs computation. It's much more computationally intensive. It needs more effort in so many ways. And so you will have to make a trade off and figure out what is it that you want to see, and what is the lowest cost, lowest effort, like, kind of, in terms of, like, how most compact, easy to use. There are several of these criteria. What is it that the doctor needs? And once you make a decision about that, you don't need to make anything more complicated. You could, as an in principle, there is no reason, like, technologically you could, but do you want to do it as a matter of, like, you want to use, so it needs a bigger room, it needs a bigger power supply. This can be handheld, it can be run from a battery, it can be portable. So there are all these other considerations which come into the picture, which will, that's, like, those are kind of very important as well. It's something which we don't think about in the beginning, but once you start interacting with doctors, you will realize that, kind of, to give you a slightly different example, say you're in the operating theater or a surgical room, right? It has to be kind of there, uh, like, completely clean. There are standards for how clean. There can't be bacteria. There can't be infectious things. So it's cleaned very extensively in any operating theater, because you're cutting open the body, and so it, like, you having to, like, the device that you're making has to be sterilized every time you use, or kind of. So there are things of that sort. How corrosive, like, and putting something in a harsh chemical can destroy, like, it, for example. And then in an operating room, you can't, the longer you keep the patient open, the more chances of infections, all kinds of problems will occur. So you are given, like, you have to do this procedure in 1 minute, and that's it. There are criteria of that sort. Like, the entire thing that you, whatever the imaging you have to do, there is a time limit on that. So you may have other constraints which are far more than resolution or something else. There are practical things of that sort which you will have to, which are important, which kind of are, kind of, which guide how you make it and what you make. Any other question? Okay. So the next topic I wanted to cover is what is called nuclear medicine. Okay, so this is yet a completely different way of getting images from inside the body. So the first version which I'll talk about is a 2D version. Okay, so where, like, so this is some, like, you this typically requires something which is um, contrast agents directly. So if some part of the some organ in the body. You swallow something and it goes into the body to the right organ, and it's like kind of in gamma rays. Okay, and this of course requires you to have radioactive materials, so it can't be done anywhere and everywhere. It's much more difficult to do. But if that's the only way to detect a disease, you have to do it. Like so, like depending on the disease, it may be expensive and so on. But so it's not used as much, but it's still a very kind of incredible that people have figured it out. Okay, so so here, uh, excuse me, sorry, yeah. So what's happening here is, so you have, uh, oops, sorry about that. So what's happening here is that you have a source of gamma rays which is sending out a ray, and you put a pinhole here, a pinhole camera, and you put a array of detectors. So each dot here goes goes through the pinhole and gives you a detector reading. So this is like a plate where it detects the radiation emitted here. So although this is an object XYZ 3D, it goes through the pinhole and you get a 2D image. And this is an integral of the path that it takes. So if the source of radiation could be anywhere from here to here, and that will give you one value at this location. Okay, and another kind of point anywhere from here to here, it goes through, and you will get one dot over here. So basically, this is an integral. The data you get is an integral of this and this. Okay, and so you get an image of the star, like what is going on inside the body this way. And so this is basically, it's a line integral of the projection through the object. And the source usually represents a selective uptake of a radio labeled pharmaceutical. So you like drink something which or inject something which has radioactivity, and you measure the radioactivity over time, and that gives you an image of the organ that you're interested in measuring. Okay, so this is so it there are problems with it. One is that it depends on the size of the pinhole. You is limited. You have a very big pinhole. Yes, sure, please go ahead. uh, what are the two different velocities you mentioned? Ah, that's an interesting question. It's the velocity in the direction of the sound. It's like so. It's basically how light sound goes and comes back in. It's there is a directionality to the. It's not speed. It's velocity. Yes, there's the directionality to this sound that comes back. These are k vectors, like a vector. These are vectors which we're taking about. I didn't want to go into too much detail, but yes, that's a good question. Yeah. So coming back to nuclear medicine, one of the challenges is that the larger the pinhole, the better the signal to noise ratio, the more photons go through, but the lower the resolution. The pinhole, the worse the more the blur. So why is it like that? So if you have a something that emits radiation, if you have a big hole, then they will kind of this like you will get this will become a big blur here, right? Like you will get something of this sort. So if you have a very small hole, then the spot size so if you have two things which are kind of next to each other this way, all of them go through. They make two different spots here. If there are two things here and the if you have something in the same distance as this one and this, so basically if they go through this hole, if the hole is very big and if there's a blob here, the red and the green ones cannot be distinguished. If the hole is this is the size of the hole is too big. But if the hole is very small, then they can be easily separated up, right? So the pinhole determines what size, larger the pinhole, the more photons you get, and therefore better SNR. But on the other hand, you'll have a more bigger blur and therefore worse resolution in this case. And the other thing is you have to create radioactivity, right? Radioactivity is inherently, yeah, yes, large means bigger blur. Big blur, large pinhole means better SNR. That's correct. Yeah. Yeah, if you have half life, so another thing about you may know about radioactivity is that it has a half life, and depending on the chemical or material, it could cause problems, right. So it could a long half life to handle, but then they also have will also continue radiating the patient long after the procedure is done. So it could, and radioactivity can cause damage to the tissue as well. So it's kind of, you may be solving one problem, but you have to introduce something else. Okay, and then functional specificity. So basically, what this means is you have to have some pharmaceutical, like the chemical atoms or the molecules, and how you deliver the drug. How does it reach the correct place? Thallium or some different kind of chemicals that you use are kind of difficult to handle, and like there are all these kind of potential problems. And with this technology, the issue is that it's a projection again. Therefore, there's no depth information, and so the solution is what's called PET, positron emission tomography. Okay, so let me just give you a very simplistic picture of how this works. So let's say you have a source of radiation over here. Okay, yeah. So what you do is, like a gamma ray is emitted, then it's like sort of like it's emitted at a certain point when there is some kind of annihilation of and what happens is that if gamma ray is emitted, it travels in opposite directions because of conservation of momentum, travels in exactly opposite direction, 180 degrees apart, and are emitted at the exact same time. So you can figure out, if say you have a ring of detectors, a bunch of detectors all around, okay, and the person or the object is inside here. Let's say there is a dot here, it emits radiation, it goes and hits one detector, it goes and hits another detector. So if they are exactly 180 degrees apart and it takes some amount of time to reach this detector, it takes a little bit longer to reach this detector. So there is a click at one point, and a few nanoseconds later there is another click 180 degrees apart. That means that by knowing what time this one came, what time the next one came, you can figure out what this position is. So that way you can, and because they're exactly 180 degrees apart, like they're opposite directions. So you and so if it has sends it this way, so you know the time difference between where the click on one side and click on the other side, you can estimate exactly where that point was emitted, and so that way you can construct the 3D shape of the 3D shape of the entire object, wherever they are emitting this gamma rays. Okay. Yes. We can have an array of detectors, and in fact they have to be stationary. Like we don't want them to be moving around. We just keep them straight. It's a ring of detectors, and you are in between. Yeah. Hmm. It will be inside. It will be from the organ which you are imaging. Sure. Yeah. Sources inside the object. Hmm. So no, it'll be like X-rays, equivalent of anything. But that so then you're measuring absorption coefficient. So what you're like here, you're not relying on the absorption properties of the material. You're localizing it using the properties of the gamma rays, which are delivered by like swallowing the contrast agent. So the way the so this comes back to my like first slide or second slide over here, where what exactly you're measuring determines the like ideas you use to get the 3D structure. So if you're interested in measuring absorption coefficient, you do one thing. If you're interested in measuring some other properties, the distribution of say these kind of particles inside the body, that's what you are trying to see. That may have we are assuming that the contrast agent you put has some importance to the disease. Say thallium, if you're India, that kind of is there in the is going into the bloodstream and going to the correct organs, and that imaging of that radioactivity is important to a particular disease. That's like essentially you're guided by the final outcome of what you want to look at and why you want to look at it and what it tells you about the disease. That's the crucial thing which decides what approach you use. Okay. Any other questions? Okay. So the next imaging method I wanted to discuss was what's called MRI or magnetic resonance imaging. Uses another kind of an approach. So it uses basically magnets. Okay. So the nucleus of an atom has a spin, and the spin results in magnetic field. Okay? But because most of these atoms are oriented in all different directions, so the magnetic moments of all of them are completely random. Okay, in any natural like kind of situation, the moments cancel each other out, and therefore there is zero effective like magnetic moment. Okay, so and in this case, the because you have water everywhere inside the body, and water has H2O, right? So it has hydrogen. It's the hydrogen nuclear spin that we are essentially interested in. It is the distribution of the hydrogen nuclei inside the body that we are looking at. Okay, so these yeah. So when you apply a very strong magnetic field, they uh, these moments tend to align the direction of the magnetic field. Okay, so this creates magnetization inside the body. Okay, and this is the tissue property that we will measure. And so MRI takes images of this magnetization inside the body. That's really what the MRI is measuring. Okay, so the way it works is you apply a magnetic field, and one of the discoveries that people made was that uh, the frequency. Okay, so what like the experiment, you apply a magnetic field and RF excitation, radio frequency excitation, and because of these like magnetic moments, you get a different frequency of radio frequency wave back. You measure the frequency of this radio wave, you can and the important thing is that the frequency that comes back is proportional to the magnetic field. So higher the magnetic field you apply, the bigger the change, the bigger this frequency that that comes back. Okay, so how do you make a 3D imaging instrument from this idea? This, this fact that the radio frequency that comes back is proportional to the magnetic field. So this was again a Nobel Prize winning idea. What the scientists figured out was that, so inside the human body, apply a gradient of a magnetic field, high, like, and lower and lower and lower until low. Okay, so now if you send a radio wave and you get a frequency back, the highest frequency will be where the highest magnetic field is. The slightly lower frequency will correspond to a slightly lower magnetic field. So different depths correspond to different frequencies. So by getting the sequence of frequencies there, so you send one frequency in, you look at the frequencies that come back. So whichever, like, the different frequencies that come back correspond to different depths, and therefore it's a combination of different frequencies. Take a Fourier transform or inverse Fourier transform of that, you know what the depth location the signal is from. Okay, that's essentially the idea. Yeah. Mm-hmm. 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 Oh, you go in a, so you go along different so let me, maybe this figure kind of should help. Okay, so yeah, so different positions along X. So basically the magnetic field strength is low here and high here. So if you get radiation from here, it should be from this position, right? And if it's higher, it will be like, so as you go higher and higher, it will go deeper and deeper inside, and then you get a signal of this sort, which is a combination, like something which has, it's a time signal. You take the Fourier transform, you get a position, like frequent, like you get a frequency signal. Frequency corresponds to, is proportional to time, proportional to X position. Therefore, you get the position. Yeah. So what's, can you repeat? Sure. Mm-hmm. Mm-hmm. Yes. Exactly. So you have radio frequency as well, right? You localize that into in one. So you have the magnetic field, and then you select one Y slice by using the localizing the RF to one location. So you have one thing which is like this, another thing which cuts like the perpendicular. That way you can kind of know only it's only coming from this place, and you can kind of, you can, so you combination of the magnetic field and the RF, you can localize it. Remember from last time, like it's not just the source, not just the first one, like intersection of two cones or intersection of two things can allow you to measure like a specific location at once. That's the idea. Okay. It's not a gradient, but it's like one is like a focused beam. Yeah. The magnetic field has a gradient. The RF, you have, so these are, of course, like this was discovered in 1970s, and over the past 50 years people have like kind of figured out exactly how to do this, like how to optimize it, like how exactly to create the magnetic field, how to create this RF like coils and so on. So people have worked on it for a long time, both in academia, like in universities and in industry. and figured out exactly how to do it optimally to get the best quality data. Any other question? Yeah. Mhm. Oh, yeah. So, let me repeat that question. X-ray sees bones. What, like MRI, what do we see is that, yeah. So, MRI is basically a measure of the density of protons or hydrogen atoms. All like so water has a hydrogen, right? So like all tissue has its organic molecules, proteins, everything has hydrogen. Most of, in fact, like the largest number, like the most abundant atom in the body is hydrogen, right? So therefore, it's a distribution of hydrogen, and therefore you can, like by measuring hydrogen distribution, you are measuring the tissue shape, like the structure and the shape of tissue. So in some sense, the more dense it is, the dense, like it's also also another kind of measure of density of some sort, density of hydrogen atoms, but density nonetheless. Okay, so since most organic, like most of the literally the entire body is made of organic molecules, and organic molecules have hydrogen all over the place. Therefore, measuring hydrogen will measure the structure of the organs directly. Yeah, that's the contrast that they are getting, and so most tissue has contrast with respect to MRI. It may not be like the contrast may be less or more, but there will be some contrast for most organic molecules, which is most of the body. Okay. So this is kind of like, so this MRI is also used in a lot of places. For example, to measure the heart, for cancer, for strokes, for like the brain, for different joints, lungs, and so on. So basically, like there are it's quite expensive. Of course, the resolution that you can get from MRI depends on the magnetic field. And the higher the magnetic field, the better quality images you can get. But making magnetic fields is it requires superconductors. It requires a kind of very expensive kind of cooling and kind of lot of different things. And yeah, of course, and the resolution is typically of the order of millimeters, like hundreds of microns to millimeters. So it's kind of low relative. You can see the entire body, but at low, relatively low resolution. If you want to see very small things, this is not the way to go. But you can see a lot of different kinds of things with this basic approach. Okay. So this is, I wanted to pause here. I think this is a good time to take a 5 minute break. Yeah, let's take a short break and I'll get